Hello students, how are you all? I hope you are doing absolutely great. So welcome all of you at AriserTalent, and we were discussing about the magnetic effect of the electric current. So magnetic effect of the electric current, in our previous lecture we have discussed about the Aristot experiments and we came to the conclusion about the snow rule, that what snow rule basically specifies. So the snow rule basically tells us about that when you kept that position of the current from south to north and you are placing a compass needle or the magnetic needle over the conductor, then the direction of the magnetic deflection will be in the west side. So this is what the snow rule specifies. Now in this category we also have one more rule that is known as Ampere's swimming rule. So what Ampere's swimming rule specifies that, let us look at the diagram here. So this will be our basic Ampere swimming rule. Now, what you can conclude from this diagram, let us understand the strategy strategy for this diagram. In Ampere's swimming rule, you can see a man or a person. Here it is a child. He is a child. So this child is swimming in this direction. It means the child is swimming in the direction from south to north. It means I can say that the direction of the current will be this like this. It means it will be from south to north. Now, if a child or a man is swimming in this direction and I can see that this magnetic needle, this is kept under the conductor. It means conductor is placed in the upper part of the side and this needle is placed in the under beneath. It means it is under beneath and I am considering that the conductor is placed here. Now, if this child is swimming in this direction, then what's Ampere's swimming rule basically specified that if the child is swimming from south to north and you are just kept the magnetic needle under the beneath of a conductor, then the magnetic deflection will be shown by the left hand. And this left hand will show you the direction that will be in your north side. So this is how you can specify the direction of the current, direction of the magnetic needle and the position of the wire by also the Ampere's swimming rule. So it is again a very interesting rule like snow rule which will give you the three specifications here. So in this rule what actually happens here, a man is swimming in direction of current. It means a person, a child or a man is swimming in the direction of the current. This is the direction of the current we have, such that current will be entering through his feet and leaving through his hand. It means current is entering from here and there will be an exit point of the current. It means current is entering from his feet and it is exiting from his palms. So, such that current is entering from feet and leaving from the palms of the hand. So this is how this situation is working. Now what you have done, you have just kept, this is your magnetic needle, this is our magnetic needle. Now what you have done in this system, the magnetic needle is kept underneath the wire. It means the wire is placed above and the magnetic needle is placed underneath the system. So the next point will be magnetic needle is placed underneath the wire. So we are assuming that the conductor is placed above the magnetic needle. Now if the man is moving in the direction of the current and the magnetic needle is placed underneath the wire, so what will be the direction or what will be the deflection shown by the magnetic needle? The magnetic needle is going to show deflection in the left hand side. it means the left hand of the person will going to show you the direction of the deflection of the magnetic needle. So, deflection of magnetic needle can be identified by the left hand of the person. By the left hand of the person, and in this diagram, the left hand of the person will going to show you the deflection of the magnetic needle. If it is going in the north direction, then the deflection will be in the north direction. So this is how the Ampere swimming law works, as same as the snow rule we have. So these are the two basic laws which will give you the direction of the three quantities. It means firstly the direction of the current, secondly the position of the conductor you have placed, and thirdly how the magnetic needle will going to show you deflection. So this is all about the Ampere swimming rule. Now let us start our new topic, that is about the magnetic field due to the current carrying conductor, magnetic field due to a circular coil, and what will be the magnetic field in case of a solenoid. So we will study these topics in our today's lecture. So just copy this from here. Now you will calculate that how will be the magnetic field be obtained in case of the straight wire, in case of the circular coil, and in the case of the solenoid we have. So in our today's lecture, we are going to determine the magnetic lines of force, and we will here consider basically the three cases, and these three cases will be straight conductor, secondly we will calculate about the circular coil, and third case will be our solenoid. So the three cases we will consider here for calculating the magnetic lines of the force or magnetic effect. Now firstly I am consider the case of magnetic lines of force or magnetic effect in case of a straight conductor. Suppose we are having a straight conductor and it is carrying a current. If straight conductor is carrying a current, then definitely it will going to show you the magnetic deflection, and you have to determine the direction of that magnetic deflection. So let's check here what will be the direction of the magnetic lines of force. Magnetic field in straight conductor. So for considering the straight conductor, let us draw a diagram here first. Firstly, I have taken a battery here, and from this battery we have connected a straight conductor. Now, this is a magnetic field in case of the straight conductor I am obtaining here. Now what will happen in this case? Firstly, you have taken a straight conductor. Suppose I am naming it as AB. This is our conductor. Now, if this conductor is connected with a source of battery, we can say that the current I will be flowing in this conductor. Then, the magnetic lines of force we are getting due to the straight conductor will be circular in shape. So, you can see that how you are getting the lines that are circular in shape. These are the circular lines that I am obtaining due to the straight conductor in a plane here. Now, this magnetic lines of force are always going to be perpendicular to the length of the conductor. You can see that these are the magnetic lines of the force in a plane, and this is a straight conductor which is exactly perpendicular to the magnetic lines of the force, and these magnetic lines of the force is going to be increased from the center of the conductor here. So this is how the magnetic lines in case of the straight conductor is achieved, and the nature of these lines will be that these lines are actually the circular in shape. So I can write here magnetic lines of force due to straight conductor will be circular in shape. It means these lines that I have formed here will be in circular shape, and the plane of these lines, it means the plane of these magnetic lines will going to be perpendicular to the length of the conductor we have. So, magnetic field lines plane will be perpendicular to the length of conductor. So in this case, we will conclude two conditions, that the magnetic lines will be in the circular shape and the magnetic lines of force will be perpendicular to the length of the conductor. Now, how you will achieve the magnetic lines of the force direction? This we will discuss now, that how can I draw these arrows in that direction. So these are actually the direction of the magnetic field I am getting here. So how I am drawing this, I will tell you further. Now, this is the magnetic field lines in case of the straight conductor. Now, let us see that what will be the magnetic lines of the force in case of the circular coils we have. So first, just copy it from here. Now, let's see the magnetic field lines in case of a second case, that is our circular coil. Now, in case of the circular coil, how you will achieve the magnetic lines of force? So, let us draw a diagrammatic representation again here. So, firstly, let's see how will the magnetic lines of the force will be in this case. Now, this is the diagram for the magnetic lines of force in cases of the circular coil. So what this diagram is representing, suppose I am considering now, in spite of taking that straight conductor which we have taken in the previous case, we are taking this circular conductor now. It means it is a circular coil. So this is our circular coil. This is what? This is our circular coil, and I have marked the direction of current in this case. It means current is flowing from this conductor like this. Now, I have connected this system with a key, that is key is closed. When the key is closed, the current will pass through the circuit, and this is our battery. So you can see that how current is going to pass in this system. So current is going like this. Now, you have to determine the magnetic field lines in case of the circular coil. So you can see that the magnetic field lines we are getting at the two ends of the circular coil. And at the two ends of the circular coil, the magnetic field lines are like this. You can see there the magnetic field lines are the and at this. Now, if I'm going to keep myself away from the center, you can see that these circles are increasing their radius. And at the center of a circle, you are getting the perpendicular lines. We are getting the perpendicular lines in case of the current carrying due to the circular coil. I'm again repeating the same point. What I'm trying to say that if I'm connecting this battery and key to the system, and when the key is closed, and suppose this pink color structure that I have drawn here is a current carrying coil. Now, in this current carrying coil, the current is flowing in this direction. So I'm assuming the direction of the current is this, that is in the anti-clockwise manner. Now, we have achieved the magnetic lines of the force at 2 points. One point is this and one point is this. This is actually what? This is actually the end points of the coil we are taken here. So the magnetic lines of the force are in the circular manner, you can see here. Now, if I am going away from this, it means if I am going away from the corners, you can see that at the center part of the current carrying coil, you are getting the lines which are exactly perpendicular to the field. It means in the center, I am getting all straight lines there. So we can say that due to the circular coil, you will get a magnetic field lines that are the straight lines we have. So, in this current carrying coil, at the center we are getting straight line. At the center we are having what I am getting? I am just getting the straight lines there. So these are the straight lines which are going to show you the magnetic lines of the force. Now, if you are moving away from the corners, at the center you are getting straight lines, and in the corners you are again getting the circles which is showing the magnetic lines of the force. Now, you will ask me that how I mark the directions of the magnetic lines of the force in this manner. So this topic I have been cleared in next lecture to you, that how I have marked the magnetic field direction, because for calculating or for marking the magnetic field direction, we have a very important rule that is known as the right hand thumb rule and the Maxwell's corkscrew rule. That will be discussed in our further lectures, but simply first understand that how will be the magnetic field effect in case of the straight conductor and the circular coil will be drawn. In case of the circular coil, this is the things we are getting here. So you just have to remember, if you are taking any circular coil, you will get the straight lines at the center, and these straight lines we are getting here will be perpendicular to the plane of the coil. So in this case, magnetic field lines will be perpendicular to this plane. In this plane, these lines are actually the perpendicular lines we are getting. So this is about the magnetic field lines in case of the circular coil. Just copy this diagram from here so we can proceed to our next part. Now, before discussing solenoid, we are left with the third part, that is our solenoid. Let us check that how you will determine the direction of magnetic lines of the force. So for determining the direction of magnetic lines of the force, we will use a very important rule that is known as right hand thumb rule. Now, what does right hand thumb rule basically signifies? So actually right hand thumb rule is used to determine the direction of the magnetic lines of the force. As I have drawn two diagrams earlier, I have mentioned the direction of the current there, I have mentioned the direction of magnetic field there. But how this magnetic field direction has been achieved? This is actually achieved by the right hand thumb rule. Now, what does right hand thumb rule specifies? What you have to do, you have to take the right hand. So your right hand will going to show you the direction of the magnetic field as well as the current. So what I have to do, I have to take a conductor here, and if I am holding the conductor like this is my right hand and I am holding the conductor like this, then curling of finger will show you the direction of magnetic current, and the thumb is going to show you the direction of the current, and curling of the finger will going to show you the direction of the magnetic field. So this is how the right hand thumb rule works. So let's discuss here that how you will see the direction in this case. So firstly, due to straight conductor, let us check the direction here. Okay. Now, this is a straight conductor that I am holding. Suppose I am holding the conductor like this. So, this is my right hand and I am showing you how actually the right hand thumb rule works. This is our hand, this is our right hand. Then, you have to curl the fingers along the palm. So, I am just curling the fingers along the palm. So, if I am curling my fingers and holding that straight conductor, you can see that curling of the fingers will show you the direction of the magnetic field, and this thumb will go to show you the direction of the current in the circuit. So what will be the thumb specify? Thumb is going to specify the direction of current. And the curling of the fingers, it means the curling of the fingers will going to tell you about the direction of the magnetic field. So by curling the fingers, will give you the direction of magnetic field. So suppose this is the straight conductor I have. Suppose I am taking the conductor like this. Now, this is our straight conductor I am taking. Now, if this straight conductor I am holding in my right hand, I am just holding it in my right hand, and I'm holding it in the right hand and just I'm curling my fingers. I'm curling my fingers and holding the thumb straight. It means we will keep our thumb exactly straight. Then if I curl the fingers from west to east, or I can say that if I'm curling my fingers in the anti-clockwise manner, suppose I'm saying that this is the anti-clockwise direction, then this point is pointing towards the north, so we can see that the direction of the current will be north. If the direction of the current will be north, then this curling of the fingers will tell you that the direction of the magnetic field will be in the anti-clockwise direction. So this is how the direction of the current and magnetic lines of the force can be achieved by using the right hand thumb rule. Now, let us see our second case we have. This is our case number 1. Now, what exactly happens in the case number 2? Now, let us see that how will be the case 2 will be there, that what will be the direction of current in the second case. So, in this diagram, we are just now, this is how the case 2 works. What we have done in this case, we have taken the length of the conductor like this and we have taken the 2 circular coils here. Because the first case we have studied about the straight conductor and second case we have taken about the circular coil. Now, how you will represent the direction of magnetic field in this case? Now, what we are doing, we are curling the fingers of the right hand, not like this. We are curling the fingers like this. It means I am curling my fingers like this, so I am holding the conductor like this. Now you can see that if I am curling my fingers like this and I am holding the conductor in this manner, then what will be the direction of current in this case? The direction of the current will be not north and south, it will be along this side, and this is our east. So if I am holding the conductor like this, then this thumb, that is the straight one, is going to give you the direction of current in this case. So I can say that if I am holding the conductor like this, then the direction of the current will be in this manner. And we are holding like this, so the direction of the magnetic field will be like this. So if you are holding the conductor like this, it means this is the magnetic field and this is the current. And if I am holding the conductor like this will be the direction of magnetic field and this will be the direction of the current. So this is a very simpler rule which is going to give you the direction of both. Now, in case of the circular coil, I am just holding the conductor like this. It is like this. If I am holding the conductor like this, then this will be the direction of magnetic field and this will be the direction of our current. So, right hand thumb rule is over here and it is a major rule which is going to give you a direction of the current and direction of the magnetic field as well as. So, B here I have denoted is actually the magnetic field because magnetic field is usually denoted by the symbol B here. So, this lecture is over for today. We will deal with the magnetic field of solenoid and many more topics in our next lecture. Thank you so much and have a nice day.